Okay, guys, now that we've looked at single loop circuits, we're going to take a look at multi-loop circuits. And here's an example of a multi-loop circuit. It's called a multi-loop circuit because, as we can see, there are 3 loops here. I could draw a loop here, this lower loop, and then there is this upper loop, and then there is the outer loop, we could think of it. So 3 separate different loops, closed circles, or closed circuits here. I might ask a simple question, and there would be then 2 different ways that we'll go through of how to answer the question. The question, like before, it might be like, I might ask something like, what's the current through the battery? That would be a fairly straightforward question to ask in this situation, and we'll see there are a couple different ways of answering it. So the first way of addressing this would be to say, okay, so maybe I'll say method 1, is to reduce the 3, or it could be more than 3, reduce all resistors to 1 equivalent resistance. In other words, could I try to take this complicated arrangement and reduce the entire arrangement to a situation where you just had a battery and 1 equivalent resistor? And in this particular case, we could. There is a way of doing it. Now, you can't do this first method in all cases. Although I will say that if you can do it this way, this is the preferred maybe method of trying to answer this question. So I've got 3 different resistors, and if I take a look at the lower loop here, these two, the 2 ohm and 3 ohm resistor, are in series, and I know how to deal with that. But when I look at these 2, the 3 ohm and the 6 ohm, these 2 are not in series with one another. In other words, there is a direct path. If I look at the 3 ohm resistor, there's a direct path from both ends of the resistor to the 2 terminals of the battery. And similarly, the 2 terminals of the battery are directly connected also to the 6 ohm resistor, which is to say that these 2 are not in series, they are in parallel. So the first thing we need to deal with is how do we add up, or how do we combine 2 resistors that are in parallel? And without going into all of the nitty-gritty detail, it turns out that it's the exact opposite of the way we would do parallel capacitance summed up. So maybe just to remember from last video, the resistance equivalent for resistors that are in series was just the simple sum. So this was the series equation. But now what we're going to see is the equivalent resistance for resistors rather, that are in parallel is the reciprocal sum. So this is the parallel. And this is exactly the opposite arrangement that we saw in capacitors. In capacitors, when you had series capacitors, you did the reciprocal sum. And when you had parallel capacitors, you did the simple sum. So a little bit confusing. You just have to remember, are you dealing with resistors or capacitors? You could also sort of maybe think about it logically. If I had 2, if I go back to the situation, if I have 2 resistors that are in parallel, since any current, if I imagine a current arriving at this junction right here, since that current can go through either the 3 or the 6, since it has 2 paths to go in as it traverses the circuit, since it has 2 options, having 2 resistors actually reduces the resistance. And that's what the reciprocal sum does, is it reduces the resistance. I will note that there's a simpler way of writing this. I can write the equivalent resistance. Another way of writing this is R1 times R2 all over R1 plus R2. That's another way of writing this. So this is another expression for parallel parallel addition. So we have these two different relationships, and we're going to use both of them here to evaluate this multi-loop circuit. So where to go? Now that I know that, where should I go? I want to reduce all of these resistors here into one equivalent resistance. And the question I might ask is where to begin. So maybe you might think, oh, well, maybe I should combine the 2 and the 3. And that actually won't work because the resulting equivalent resistance between the 2 and the 3 would not be entirely in series or in parallel with the 6 ohm resistor, because the 2 ohm is in series with the 6 ohm, but the 3 ohm is parallel with the 6 ohm. So we can't do it that way. However, you may note that we could take the 6 and 3, which are in parallel with each other, and both of which are in series with the 2. We could combine the 6 and the 3 first, and that's the right way to do this. So let's do that. So I'm going to combine the 6 and the 3 by saying REQ is equal to 6 times 3, or 18, divided by 6 plus 3, which is 9. So that's 2 ohms. And so what I've just done there is I've said, okay, well, I can combine these two into one resistor of 2 ohms. The 3 and the 6 can be combined into one equivalent resistor of 2 ohms, which is then in series with the other 2 ohm resistor. So now I've got a 2 ohm equivalent resistance here and the 2 ohm resistance here, and the REQ, the equivalent resistance between those, is just 2 plus 2, which is 4 ohms. So that tells me then that the total resistance here, R total, for this whole circuit is 4 ohms. In other words, I can think of this multi-loop circuit as though it were a circuit with the battery of 12 volts and a single 4 ohm resistor. And then to calculate the current from there is fairly trivial. I can simply say that the current is equal to the voltage divided by the resistance, or the EMF divided by the resistance. And that would give me 12 over 4, or 3 amps. So that's method 1. We'll get to method 2 in a minute. I just wanted to maybe point something out, and that is, actually, let me pause for a moment and just try to clean up my picture here, because we're going to go back to this this original arrangement in a minute. So I'm just going to get rid of some of this other stuff up here. I could ask other questions other than just the current through the battery. So for instance, I might wonder if I think about this junction right here, before we get on to our second method. If I think about this junction, I noted this before, but there's a current that comes out of the battery down here, and I'm going to call that I1. So that current comes out of the positive terminal of the battery, conventional current, and it goes through the circuit. It goes through the 2 ohm resistor, and then when it gets to this point, it's going to split. You're going to have a current going here, I'll call that I2, and another current going in this direction, I can call that I3. And this might be obvious to you, but if we compared I2 and I3, since the 6 ohm resistor is bigger than the 3 ohm resistor, there's going to be more current that would go through the 3 ohm resistor. In other words, you would get twice as much current going through the 3 ohm resistor as the 6 ohm resistor, because it has half of the resistance. And what that means is, of this 3 amps that we noted before is coming out, I1 is 3 amps. We know that already. That means of that 3 amps, I'm going to get twice as much of the 3 amps going through here, what we called I3. So that would be 2 amps, and only 1 amp, half as much, going through the 6 ohm resistor. And what we've done here is I've just invoked the second rule. I mentioned Kirchhoff last video. This is the second rule of Kirchhoff. This is Kirchhoff's junction rule. And this is just really a restatement of the conservation of electric charge. So, and what this says is, if I think about it, if I take a look at a junction, that's what this thing is. This thing right here is a junction. Then the total amount of current that goes into the junction has to equal the total amount of current out of the junction. So as we just were sort of noting, if I'll come in here and draw, if 3 amps comes in, 3 amps has to come out. So in other words, I2 plus I3 has to equal I1, which it did. We had 1 plus 2 equals 3 amps. So that's the junction rule. And again, it's just conservation of charge. We couldn't have a certain amount of charge coming into the junction and a different amount of charge leaving the junction, because that would mean we either gained or lost charge, which is not allowed. All right, well, let's, I promised you another method of thinking about this, so let's think about this other method. And again, I'm going to go ahead and kind of simplify things. I'm going to pretend that we haven't learned this other method, so we don't know all of this stuff about the different currents, I1, I2, and I3. And maybe I'll actually just go ahead, if I can, and erase all of this stuff down here too. I want to see if I could find the current through the battery a different way. And that way is going to be using the loop rule. So this is going to be method 2. Use Kirchhoff's rules. And there's sometimes, this is not the easier way to do it, I'll promise you that, but there are some times in which this is the only real way to evaluate a complicated multi-loop circuit. So let's show how we're going to do this. So as I mentioned before, there are 3 loops. There's the lower loop, there's this upper loop, and then there's the outer loop. So there are 3 loops. And what I'm going to do is I'm going to write loop rule equations. And remember what the loop rule says, that the total voltage across a closed loop has to be 0. And so I might start right here, maybe. Call that point A right here. And I'm going to imagine moving through the first lower loop. And so I imagine if I started at A and I moved in the direction of the conventional current, if I imagine an individual charge, it will gain 12 volts. And so I'm going to start my loop rule equation by saying, all right, as I move in that lower loop, I'm going to say I gain positive 12 volts as I move across the battery. So again, I'm imagining this being some little positive charge that's moving, gains 12 volts as it crosses the battery. It's then going to lose some of that energy when it goes through the 2 ohm resistor, and the amount of energy it loses is the current times the resistance, I times R. So now I'm going to write minus I, which is 2 ohms, times, I, which I'm going to designate that as we did before as I1, times the resistance, which is 2 ohms. So whatever I1 is, and we already know it's 3 because we already did this, but we'll pretend we don't know that the current there, I1, is 3 ohms, or 3 amps rather. But we do know that that current multiplied by 2 is going to give us the total potential drop across this resistor right here, this one here. So then if I continue going here, what's going to happen at this junction, of course, I'm going to get a different current. And I think we chose to call this, I think we called it I2. I forget, but I'm going to call this current I2. So in my world, this is going to be I1, I2, and I3. So we're going to get another drop, potential drop across the 3 ohm resistor, and that's going to be equal to I2 times 3 ohms. So minus, because I'm losing potential as I go through the resistor, I'm losing some energy, minus I2 times 3 ohms. And then if I continue going, I get back to my starting point. So this all equals 0. So there's an equation. That's a first equation. It has 2 unknowns, so I can't solve it. So I need to start trying to write another equation. So maybe I'll start at point A again, and now I'll do the outer loop. So I get positive 12 as I go across the battery, minus I1 times 2. And then when I get to this junction, now I'm doing the outer loop here. So now my current is I3 as I go across the 6 ohm resistor. So I could say minus I3 times 6 ohms. And that's also equal to 0. So that's two equations. And now let's think about what we have for unknowns. We know that we have I1, I2, and I3. So I have two equations with three variables. I can't solve, I need a third equation. There are other equations we could write. For instance, probably the easiest way to go from here is to use the junction rule and note what we noted before, which is I1 has to equal I2 plus I3. That's probably the easiest third equation, but I want to just note that I could write a fourth equation. I could write a loop rule equation for the top loop, which is going to look a little bit strange. So maybe I'll start here right at the junction, and I'll move in this upper loop in clockwise direction. So that's going to be, I'm going to get minus I3 times 6 ohms. And then if I go in this direction here, I'm going to get minus I2 times 3 ohms, and then I get back to the junction and I get to 0. And you might be wondering about this equation because this equation looks pretty weird. I have two negatives adding up to 0. But of course, what you'll notice I was moving in the counterclockwise direction of my loop, but we know that I2 is going to be in this direction. So I have actually used the loop rule opposite from the direction that I know the current is really moving at through this 3 ohm resistor. All that means is that when I do this equation out, if I were to use this fourth equation, I would end up with I2 as a negative value. And that would just tell me that the direction was opposite of the direction of the equation that I used the loop rule for. So now I've got four equations with three unknowns. I can certainly solve four equations with three unknowns. I might go ahead again and maybe just use the first three and I'm going to ignore this one for now. You could use it, but I'm just going to ignore that one for now and just plug in this relationship that wherever I see an I1, I'm going to put I2 plus I3. So I'll sub I1 plus I3 in, or I2 plus I3 in for I1 here and I1 there. And then I'm going to get two equations with two unknowns. So what's that going to look like? It's going to look like 12 minus 2I2 minus 2I3 minus 3I2 has to equal 0. So this is the first equation. I just subbed in this here in for I1 and distributed the 2. And we can simplify this equation, and this is going to turn into 12 minus 5I2 minus 2I3 equals 0. Put a box around that, save it for later. So now I'm going to do the same substitution as I did before, and I'm going to plug this in I1 plus I2 in for I2 plus I3 in for I1 right here. And I'm going to get 12 minus 2I2 minus 2I3 minus 6I3 equals 0. And this is going to simplify to 12 minus 2I2 minus, 8I3 equals 0. And now now that I've reduced this whole complicated set of equations to two equations, now I have to take this two equation with two variables and solve. Maybe the easiest way to do this is just elimination. So if I multiply the first equation, if I multiply this guy by 4 and then subtract, that should work. So maybe I'll do that down here. If I multiply the top equation by 4, I get 48 minus 20I2 minus 8I3 equals 0. And now I can just subtract these two equations. So 12 minus 48, that's going to give me negative 36 that's going to be plus 18 I2 plus 0 equals 0. which then gives me that I2 is 36 over 18, which is 2 amps, which is what I had expected to get, so that's good. So that means I2 is 2. I can plug now I2 back in. I can plug in 2 into one of these equations. I could plug in 2, for instance, up in for I2 right here maybe, and that would give me 12 minus 4. 12 minus 4 is 8, so that tells me I3 is 8 over 8, so I3 is 1 amp, which we knew it to be true, so I3 is 1 amp. And then finally, I can go ahead and take this equation up here and say that 2 and 1 has to equal 3, so I1 is 3 amps. So that's a much longer way using Kirchhoff's rules to solve this particular multi-loop circuit, because we found the first method did work. But I just wanted to point out that, or I wanted to show you that in some cases you have to go through this sort of laborious, slow process of writing multiple equations using the loop rule and the junction rule, and then solve the system of equations.